1985 at a price of $950. In exchange for your hard-earned wages, you received a hefty piece of ceramic studded with tiny gold pins. If you were to remove the protective metal cover, as we are today, you'd find a sliver of silicon no larger than a postage stamp. And on that wafer, over 1 million tiny transistors. When viewed with a normal optical microscope, you can see a vast array of lines snaking across the wafer. These are aluminum interconnects, microscale wires that serve as a global highway to information and power flowing across the wafer. In between the aluminum are splashes of vibrant color. This is light diffracting off the surface of the wafer, or rather, diffracting off the complicated stack of silicon, oxides, and thin metal films. Together, these layers diffract light into a rainbow of colors that you see. Along the periphery are blobs of gold attached to delicate bonding wires. These serve to move data and power onto and off the silicon wafer, communicating with the outside world. We can use a different instrument, an atomic force microscope, to understand how tall these aluminum interconnects really are. This instrument scans a tiny probe across the surface, collecting height information, which can be converted into a three-dimensional model. From this data, we can see that the features are only about 2 microns tall and about 4 microns wide. Popular science media likes to use the width of a human hair as a size comparison, but at around 80 microns, I'm afraid we are well past that being a useful metric. A human hair is just too large in comparison to these features. A more appropriate metric would be the size of a bacteria, which are just a few microns wide. Earlier, I mentioned that integrated chips are stacked in multiple layers. If we move over to the scanning electron microscope, we can begin to see some of that structure. You might notice that the underlying layers influence those above it. The surface is wavy, where one trace passes over the other. This seems counterintuitive. You'd expect the surface of a precision device like a silicon wafer to be ultra-flat. But in reality, as layers are deposited one on top of the other, the surface becomes increasingly rough, as each subsequent layer distorts the surface a little bit more. Modern chips deal with this by polishing the surface periodically throughout the fabrication process. But older chips did not require this as much, as they're a lot less complicated. The small circles you see scattered around are vias, vertical plugs of metal that connect different layers together. And while all the features feel very geometric and mechanical, once you zoom in enough, everything is slightly rounded and surprisingly organic feeling. The truth of the matter is that it's just hard to manufacture precise right angles at this scale, and everything starts to get a bit rounded. We can switch to a different detector on the scanning electron microscope that allows us to peer beneath the surface a little better. This allows us to see and map the underlying layers in better detail. The 486 only has a handful of layers, but modern CPUs might have dozens stacked on top of each other. I wanted to see if we could view the transistors themselves, which would be buried at the very bottom of the stack. But the only way to access this layer is by cutting the chip apart and grinding off the upper layers to get at the lower layer. Despite my best efforts, the polishing process looks pretty crude at the microscopic level. But crude attempt aside, we can see some of the layers starting to emerge. Likewise, a cross-section shows some interesting details. To help understand what's going on here, we can enable a detector that identifies different atomic elements in our sample. At the bottom is the silicon wafer, as you'd expect. But do you see how there's a dark area and a lighter area above it? If we enable the oxygen layer, we can see that it overlaps with the lighter silicon. This is silicon dioxide, 2 oxygens for every silicon. Oxide layers are used as an insulating layer in transistors because they're easy to grow.